Hello, good evening everyone. Myself Khadar Basha. Welcome to ACE Online by ACE Engineering Academy. So today we are going to discuss some important concepts regarding DC machine. So in that there are so many topics uh, which are useful for competitive examinations. Now in that today we are going to see about braking of motors, electric braking of motors, DC motors. First, what is the need of brake in motors? Tell me. What is the need of brake? So, in order to stop the motors, maybe you will get doubt by removing supply also we can stop the motor. But generally if you go to manufacturing side, industries, so we need to stop the motors regularly there in order to protect the loads or in order to avoid the problem whatever to be occurred. So we need to stop the motors immediately. If you remove the supply, it will comes to stop, but not immediately, no. It will take some time. Maybe it will take 30 seconds or 40 seconds or 20 seconds based on the kinetic energy stored in that. But using brake means we need to stop the motor as much as possible earlier, like 2-3 seconds. We need to stop it so that the loads are protected. Okay, regularly we apply brakes. So we have so many types of brakes, like mechanical brakes, so many types again, and electrical brakes. Now we are going to see here today how to apply electrical brake in DC motor. So mainly in electrical braking we have three types again. Three types. What are the three types? Yes. First one, dynamic braking. We also called rheostatic braking or resistance braking. Dynamic or resistance braking, also called rheostatic braking. Okay. And second one, plugging or reverse current braking. So this is most popular. Plugging or reverse current braking. Reverse current braking. Next, third one is regenerative braking. Regenerative braking. From braking also we can expect regularly one question from the competitive examinations like any state electricity boards. Now, first in all these braking methods, what is the main criteria we need to apply? Generally under running condition of motors, what is the direction of torque? Whatever, suppose torque direction is clockwise. In which direction motor rotates? Clockwise only it rotates. But if you want to apply electrical brake, during that we need to reverse the torque in motor. Assume that motor running at 1000 rpm. So while it is running condition, we need to reverse the torque in that immediately. So if torque reverse, that torque will oppose the rotation of rotor and the speed will reduce to 0 finally. So we need to produce a reverse torque in this. For that different methods we are applying here, like dynamic control or plugging method or regenerative braking. So among these type of brakings, which is the fastest brake? Is plugging or reverse current braking. But which is the efficient brake here? Generally in all braking methods some power will be lost. Some power, electrical power will be lost. But in one of these braking, that is regenerative braking, there is no power loss. Instead of power loss, additionally we get some power generated. So power saving, at the same time power generated again. So this is most efficient brake. Okay. For the first one and second one, we need to apply or we need to provide some circuit to apply the brake. But for the third one, we need to provide, we no need to provide any type of circuit here. Directly, automatically it will takes place. Automatically it will takes place and automatically it will disappear. So small points you have to remember in each of these braking methods for any examination. So they will ask mostly how much resistance to be added to limit the current. Maybe dynamic braking, or it may be plugging, or it may be regenerative braking. But in regenerative braking we don't add any resistors. So there is no circuit provided. Okay, let's see first briefly once how to apply dynamic braking. So for this example, I am taking DC shunt motor and how it is applied brake using this dynamic. See here, first one is dynamic braking. Dynamic braking. Now, first let us consider a shunt motor which is under normal running condition. Let us consider a shunt motor. Under normal running condition it is. Let the voltage is rated voltage applied V, rated current, motor running at rated speed. Let it is rated speed. This is under normal running condition. Motor is running at some 1000 rpm or 1200 rpm, whatever it is. Now we need to provide brake, electrical brake. So as motor is considered, it is rotating in clockwise because torque is in clockwise direction at some speed 1000 rpm for example. Now we need to stop the motor immediately by applying this brake. So during this dynamic braking, we have to remove the armature completely from supply. We have to remove armature from supply. Now let us remove. To the field winding, supply will be there as it is. To the field winding, supply will be there as it is, but the armature is disconnected from supply. Armature disconnected and connected to a rheostat or braking resistor we call it is. And supply is there as it is to field winding, no change, it is plus minus. So field current will be there as it is in this ISH. Whatever flux is there previously, same flux is there here also. Now this is our braking connection. So during braking, this is the figure. But one thing here, whenever we want to apply brake, at that time we don't open the armature, we don't connect resistor. We will have a pre-arranged system here. That is a resistor across that armature we already placed readily. Whenever we want to apply brake, immediately we close the armature terminals to this resistor. Then automatically brake applied. Okay, at that time we don't open and we don't connect resistor because that will take time again. That's why. Now, previously under running condition, there is a back EMF in motor, EB. Back EMF which is opposition to supply voltage always. Now, whenever we apply this connection or brake, electrical braking using this method, immediately the speed of motor will never change. Whatever speed is there here, same speed is there at that instant. And what is the back EMF polarity? Same only. Why? Because back EMF always depends on the speed direction and flux direction. Flux is same anyhow in both, and speed, it is rotating clockwise only, same, and same magnitude. So back EMF polarity will not change. Whatever is there previous, plus minus, same will be there now also. So this is our EB, plus minus. Okay. Now, due to this EMF inside, so when there is a voltage, flux is there, armature is rotating, so it is cutting flux lines, EMF will be there, EB. Due to this EMF, a current will flow in this now, IA, armature current. How it is flowing? Plus it is minus, so current will circulate like this. This is the path of armature current. Now check what happened. Previously there is a torque in normal running condition which is proportional to product of flux and current. Okay, torque in generators or motors proportional to this. Flux is same, no change. Previously armature current is moving in downward direction, or you can take terminals A, coming from A to A. But now the armature current is reverse or not? Yes. The armature current is moving now from terminal A to A in this direction. So as armature current reverse, what happens to torque? Torque proportional to flux is same, no change, but IA become minus because reverse it is. Then what is the direction of torque? So overall it is negative. Means sign change of torque is there. Previously clockwise, now it is anti-clockwise. Whatever torque is there inside, it is coming in opposite direction. Rotor rotation clockwise only, but internal torque is opposition to it. That's why we call it is braking torque. Okay, rotation is clockwise, but the torque generated inside is opposition to that. That is called braking torque. Now due to that opposition only, the speed of motor reduces. Now speed will start decreasing. Speed decrease. So as this torque continuously acting in opposite direction, up to there is rotation, there is EMF, there is current, there is torque. Suppose speed becomes 0. Once speed becomes 0, is there any back EMF? Or is there any EMF in armature? No. EB proportional to N phi. There is a flux, but speed is 0. As speed 0, this EMF total is 0. If EMF 0, what is the current? 0 only. Then what is the torque? 0. So finally it comes to rest. But the drawback of this system is, it is the slow braking system. Why it is slow braking system? Observe. Whenever speed is reducing, EB also reduce or EMF reduce. If EMF reduce, what is the magnitude of current here? Also reduce. If current reduce, what is the torque production? Also reduce. Means whatever opposite torque is acting, that opposition slowly decrease. That's why slowly the speed will comes to 0 here. That's why it is not the effective brake. Now you may get doubt again. Then why we are adding resistor here? Suppose without adding resistor, directly connect armature, then what is the current? Once you connect directly, the armature current is IA equal to, this current IA due to back EMF, and inside we have armature resistance, EB divided by RA. If you don't add resistor, then generally supply voltage, let 220 volts. What will be the range of back EMF in that? So nearly will be there, nearly some 210, 215, that 200 volts also, back EMF. Now at that instant of braking, if EB is very high, what is the current? Very, very high, because armature resistance less than 1 ohm, very small, then current will go to very high value it is. Then if this much high current flows in armature windings, it will overheated and there is be damage to windings. So to protect that high current, we are adding this resistor. That's why we call it is resistance braking. Okay. Now totally what is armature current during this braking? EB by RA plus RB. This is the armature current equation during dynamic braking. So these current equations in every braking method important. From here only we get questions. Now you may get question, how much braking resistor required in order to limit the armature current to some 10 amperes or 20 ampere, like that. How much resistance to be added during this dynamic braking? So this is one type of questions. So totally in dynamic braking, during braking, the armature is disconnected from supply and connected to a resistor. Okay. So during that, a current will flow in armature in opposite direction of previous, because of internal EMF that current is flowing. Okay. Now you may get doubt again, why we don't call this is reverse current braking? Here also current reverse, no? Yes. But why we don't call it is reverse current? This current is not supplied by source. This current is due to internal EMF itself. That's why we don't consider it is reverse current. But the next one plugging we have, that is called reverse current braking, because in reverse current braking, we will give supply to the armature from, we will give supply directly from source. Slowest braking it is, slowly brake will takes place. That's why we don't use this effectively. For small size you can use, but for large size we need heavy reverse torque. Then we use plugging only mostly. Okay. Next, second one, let's see. Second, what is the second braking? Plugging or reverse current braking we call. Let's see how we apply this plugging in case of DC motor, shunt motor. Again, first we take a shunt motor under normal running condition, same as the previous. Consider a shunt motor under normal running condition at rated voltage. Now motor means it will rotate in some direction. Consider it is rotating in clockwise because torque is in clockwise direction at some speed n. This is the figure under normal running operation of motor. Now we need to apply brake. Let the polarity of back EMF opposition to supply EB plus minus. This is our supply polarity plus minus. This is under normal running condition. So if you want to apply plugging in shunt motor, in plugging always we need to reverse the polarities for armature, or we need to change the terminals of armature only. Okay, so this is let terminal A, terminal AA. Now reverse this here. To the field winding as it is will be their supply, same polarities. But to the armature we are interchanging terminals like this. check all of you once. There is some small technical issue now. Check it once again. Is it okay? Audio, video, all of you. Check it now once. Is it coming audio, video for all? Okay. Now, in the previous dynamic braking, so I think those, if anybody lost it, just revise once again. So during dynamic braking, the armature is disconnected from supply and it is connected to a resistor. During that, a current will flow in armature. It is due to internal EMF or back EMF in that. Now that current is flowing in reverse direction. That's why torque will reverse, and that torque will reduce the speed of motor because as it is in opposite direction to the rotation, and finally speed becomes 0. Once speed 0, EMF 0, current 0, torque 0, everything 0, then motor totally comes to rest position. But what is drawback of this braking? So in this braking, it will takes place slowly but not quickly. So we need to stop motor quickly, no? That is the main drawback of this method. Next, in the plugging, considering a shunt motor again under normal running operation it is. Now during plugging or braking condition, we need to reverse the terminals to the armature from supply itself. So here if you observe, plus is connected with the armature terminal A, but now we will change this. This is A, this is A, this is AA. Now this AA we will connect to armature plus terminal, positive terminal through a resistor here. That resistor is important and it is connected to this, okay, like this. Here armature is cross connected or reverse connected with respect to supply polarities, okay. Then a current will flow in the reverse direction here. This is our braking resistor. So here Y resistor again I will tell. This is IL. Now armature current is flowing through armature in reverse direction. Field current no change, it remains same only, same as the previous, okay. Now let the torque previously clockwise direction, motor also rotating clockwise direction, but here we need to reverse the torque in order to reduce the speed to 0. At the instant of this braking or plugging, motor is rotating in same direction at same speed. Then what is back EMF here? Same polarity. Polarity of EMF will not change immediately here because EB depends on speed and flux, no? Rotation is same direction during that braking and flux also same direction. No change in the field current and flux. So therefore EB polarity same. Now a current is flowing in reverse direction here. This is IA. Then what happens to torque? Proportional to flux and IA. What is IA now? Minus IA. Then what is the torque? Negative. Means sign change. Previously torque is in clockwise. Rotation also clockwise. But now torque reverse. This is called braking torque. But what is the rotation here? Clockwise it is rotating at that instant. Due to this reverse torque immediately, the speed of the motor drops. Now speed reduces. Speed reduce. Now quickly that speed will reduce to 0. But after coming to 0, it won't stop there itself. Now this motor will try to rotate in reverse direction because supply is there still. But in the previous dynamic braking, what is happening? In previous dynamic braking, we are not giving any supply to armature, just armature connected to a resistor. So once EMF 0, everything 0 there. And after that it won't rotate again reverse. But in plugging, that is the problem. So after coming to 0, and then it starts rotating in reverse direction because torque still produces in the same anti-clockwise direction. Now it rotates in reverse. Now that is reverse operation of motor again. But if you don't want that reverse operation, you need to remove the supply whenever it is reaching to 0 speed and then apply mechanical brakes tightly on that so that motor completely stops. then it won't rotate in reverse direction. Okay. Now here, what is the magnitude of armature current during braking? What is the current during running condition? During normal running condition, the armature current is V minus EB divided by RA. So this is our normal rated currents. But during plugging, when we apply the plugging circuit, then what is the armature current? Tell me. IA equal to, observe this figure once. Here supply polarity of, that is positive terminal, is connected with the positive polarity of back EMF. So V minus EB, that is subtractive. But here this positive terminal is connected with negative terminal of back EMF. Then what is the total voltage across this armature now? Additive. Previously it is subtractive, but now it is additive here, because armature terminals we reverse. That's why the armature current we get V plus EB divided by RA. Then why we are adding that resistor here? Suppose if this resistor is not added, then what is the current IA? Very, very high or not? Because here some of the voltages we have. Some of the voltages. Due to this reason, if current is very high, it will damage the winding again. To limit that high current, we are adding some resistor in series with armature called braking resistor. So questions regularly we are getting from this calculation of RB. How much resistance to be added in series with armature in order to limit the armature current to some value? Sometimes they give rated current, sometimes 120% of rated current or 150%, like that. So whatever they given, we have to use this equation for that. Okay, calculation of RB here, that is important. Now the advantage of this braking over previous is, it is the fastest braking, because the current is coming from supply. You can maintain high currents. When there is high current, torque in reverse direction also high, because it is proportional to IA. If reverse torque is high magnitude, quickly speed reduced to 0. But in dynamic braking, what is happening? Whenever speed is reducing, EMF reducing, current reducing, torque also reducing. Opposition is reducing slowly. That's why slowly speed reduced to 0. But quickly we can stop the motor in plugging method only. Okay. But here, after 0 speed, it will try to rotate in reverse direction. But in order to avoid that, you need to remove that supply. That care we have to take in plugging method. Okay. Now this is the equation of armature current during plugging. V plus EB by RA plus RB. Okay. Next, let us see the third one is regenerative braking, how it takes place. Third, regenerative braking. Regenerative braking. Now in regenerative braking, we don't apply any connection for this. Like previous, we changed the terminals of armature for plugging, and dynamic also we removed the armature from supply and connected to a resistor. So all this we don't do for regenerative braking. That is, consider a DC shunt motor under normal running condition. Let rated voltage V, IL, IA, ISH. Let due to the torque developed in clockwise, motor is rotating in clockwise direction at some speed N. This is normal running condition, and back EMF is induced, EB. So with example also I will try to show you now. That is, let the supply voltage is some 240 volts. Supply voltage 240. Then what will be the back EMF under normal running condition? Little less than that. For example, 235. This is. So as this voltage is higher, current direction is always from high potential to low potential, and armature current is passing in this direction. Torque is developed clockwise, for example. Then motor also rotating in clockwise direction. Okay. But sometimes due to the position of load variation, the speed of the motor suddenly may increase. suddenly the speed of motor may increase due to load effect, but not motor effect. Supply is same, fixed only. But sometimes the speed of this motor may increase. Suddenly load decreases, okay, or sudden shaft gets break with respect to load, or whatever mechanical coupling is there to the load, that is opened, means load suddenly disconnected, then motor speed will rise. Or you can take another example, trains traveling on a hill platforms, that is coming down in the hill areas. So during that downward direction, so there is due to position of that load, the trains or any rotating wheels can move at high speeds. Okay, with respect to supply, it has to move suppose 1000 rpm, but it will move more than that 1000 rpm, let's some 1100 or 1150 like that. So as it is higher speed, no, what is the back EMF proportional to? N into phi. The EMF induced in armature depends on the speed and flux magnitude. Anyhow, flux is remains same because supply voltage is same. But what is the speed of this motor suddenly rises? Then what is EMF? As speed increase, EB increase. Previously it is 235 only, but now let it is becoming 244, for example. As this voltage is now greater than supply voltage. Now what is the current direction always? High voltage to low voltage. Now as this voltage is high, current will reverse in this. IL also reverse. Now armature sending back power to source. That is only we call regenerative. Now during that here, as IA reverse, what is the torque? Torque depends on flux and armature current. Now the torque is, flux remains same, field direction no change, but IA become reverse, minus IA. So during that, the internal torque is reversed. Internal torque reverse. This is we call braking torque. This is called as braking. As speed is increased to some higher speed, immediately braking torque is entered into picture. During this braking operation, again speed decreases. Again as speed is decreasing, what is this back EMF? Again decreases. Previously 244, no. Now it will reduce below 240. So once this voltage comes to below 240, for example some 237 volts or 239 also, less than 240. Once it comes below 240, again which voltage is greater? This one. So again current will flow from supply to armature. Again as current IA reverse, again the braking torque will become normal motor torque. Again it will continue to run as a motor. Then what is the use of this braking? Yes. In regenerative braking, whenever it takes place automatically, it never comes to zero speed. Whenever it takes place automatically because of higher speeds, automatically it takes place and automatically it disappears. But it is not coming to zero speed. So in regenerative braking, two cases we have. Automatically it takes place means it never comes to zero speed. But if you want to stop the same motor using regenerative braking, so we need to change the supply voltage here. We need to change supply voltage. Without interruption of these speeds and all, we need to change supply. How? For example, I will show you here. Check. Let the supply voltage is 240 volts and back EMF generally under running condition 235. Then what is the current direction? Supply to armature, normal motoring operation that is. But if you want to stop or if you want to bring motor speed to zero totally in this regenerative braking, now what you have to do is this voltage you need to drop suddenly to some low value. Let us drop to some 170 or 180 volts, something. 170 volts. Is the back EMF will change immediately? No. Because back EMF's speed and flux, whenever voltage reduce, field current little may reduce and the speed will not change immediately, no. So back EMF totally will not reduce immediately. So it will be some little higher value. So then 170, let us take it is 235. Okay. Now this is supply voltage we reduce here directly to some low value than back EMF. Then what happened? As this EMF is greater than the supply voltage, current will reverse. Braking action takes place. Speed little reduce. Whenever speed reducing, now back EMF starts reducing. Whenever it comes to near to this point, like 167 or 160, again motoring operation. So what you have to do is, we will measure that voltages, how much EMF is there or not. So whenever it is reducing automatically, as speed is reducing, you also should reduce this voltage to some 100 volts. Whenever it is reducing, simultaneously you should drop again this voltage, such that again EB should be greater than the supply voltage, up to we get zero speed, this one. So this is, we are applying that supply voltage change, but automatically it is not taking place, no. In this case, you can bring the speed of motor to zero in regenerative braking. And during this braking, the advantage is there is no power loss, and power is regenerated back, supplied back to source. So power saving is there. But in previous two methods, we are connecting resistors, braking resistor in both dynamic braking and also plugging. So when there is a resistor, when there is a flow of current, definitely some I square R loss will take place. So power loss is there during braking operation, but there is no power loss in regenerative braking. Okay, so this is some short information regarding braking. Like that, the same methods, whatever we have, dynamic, plugging and regenerative, we can apply for series motor or separately excited motor also. For all motors we can apply this. Just example I have shown, the shunt motor. Now let's see some questions how we are getting in the competitive examinations. See that. See this question. A 200 volt DC shunt motor is running at 1000 RPM and it is drawing a current of 10 amperes and its armature resistance is 2 ohms. It is braked by plugging the resistance to be connected in series with armature to restrict the armature current to 10 amperes. The armature current should be 10 amperes only. It should not be more than that. Then how much resistance we should add in series with armature? This is plugging method, no? During plugging, what is the connection? The armature terminals, supply to armature terminals are reversed like this by connecting a resistor in series with armature. So this is the connection. Okay, we need to find out how much braking resistor to be added such that the armature current is limited to 10 amperes. Armature current limited to 10 amps. And what is the supply voltage? Supply voltage. The supply voltage is 200 volts and armature current 10 amperes running at 1000 RPM. So first calculate back EMF of shunt motor, EB. What is EB? V minus IARA for shunt motor. V is 200, IA is, so it is drawing 10 amperes given, but it is not mentioned clearly is it load current or armature current. If you take it is as load current, you cannot solve this because field resistance not given. So in such type of situation, you have to consider that is as armature current only. Okay, then IA is 10, armature resistance is 2 ohms. This is 180 volts. This is the back EMF. Now at the instant of plugging, EB remains same. It won't change now immediately. EB remains same at that instant of plugging. And a current will flow in reverse direction in armature, IA. And we have to find out how much resistor to be added to limit current to 10 ampere. Now therefore, what is the armature current equation during plugging? The two equations you should remember for dynamic braking and also for plugging, the armature current. What is the current for plugging? V plus EB divided by RA plus RB. How much current we have to limit? 10 amperes. We should restrict to 10. V 200 plus EB is there, 180 we calculated. Armature resistance 2 ohm plus braking resistor we need to calculate. A simple calculation, no need of any calculators. 2 plus RB equal to, this is 380 divided by 10, nothing but 38. Then RB, the braking resistor required is 38 minus 2 equal to 36 ohms. So this much resistance we should add. if you want to limit the armature current to 10 amperes during plugging. Otherwise, if you don't add that much resistance, current will be very, very high. So it may damage the complete armature winding. Okay. So this is on plugging. Let's see the one more question. Next. See this one. If the supply polarity to the armature terminals of a separately excited DC motor is reversed, then the motor will run under dash. To the separately excited motor, armature terminals are reversed. Okay, if the supply polarity to the armature terminals of a separately excited DC motor is reversed, what happened? So in which of the braking we are reversing the terminals to armature? Only plugging. Only in plugging the supply polarities to armature we reverse. But in dynamic braking, we are not giving supply to armature at all first. Okay, so only plugging. So on this is plugging condition directly. Okay, next. See the next question. In plugging of DC motors, connections to armature are reversed, or connection to field are reversed, or connections to both armature and field are reversed, or connection to supply are reversed. Now where we are reversing? In plugging, the connection to only armature. So I have shown in shunt motor, only armature is reverse connected or cross connected. Field winding is there as it is, no change in the field current or field winding terminals, same it is. Only armature should change. If you change connection to supply, no. So there is a shunt motor. If you change the supply polarities, it will change for both armature and shunt. But we need only armature terminals to be reversed, so that current will go in reverse direction only in armature. Then only we can call it is reverse current braking. So connections to armature are reversed. Okay. So mostly this type of questions. So there is no big difficulty to find in these questions of braking. So almost easy questions will be there, and easily we can score if given also from braking of these motors. Okay. So this is our today's topic, and we will meet some other day with some topic with questions. Okay. All the best.